I'm in the process of boiling some water to make pasta. A pretty normal everyday thing around our house. But I bring it to your attention because underlying this common activity are a number of important principles of chemistry. Principles associated with energy. We'll begin our discussion of energy by talking first about temperature and then about heat. First, temperature. We talk about the temperatures of things routinely, don't we? But what does it mean when I say one object has a higher temperature than another? For example, I know that the temperature of the water in this glass of ice water is lower than the temperature of the water in this pasta pan. It turns out that temperature is just a way of expressing the amount of motion, or more technically the amount of kinetic energy, that the molecules in the two water samples have. Now, what do I mean by that? Well, the molecules in all materials are in motion. They move from place to place, we say they translate, and they vibrate, and they rotate. Well, if you look at the molecules in our two water samples, you see that those in the ice water are moving more slowly. That's what's actually happening on the molecular scale. But the way we perceive that and express that on our big macroscopic scale is by using this temperature terminology. We say the ice water is cold and the pasta water is hot. This way of speaking comes about because of the way our brain interprets the nerve signals it gets when we touch something that has fast molecules, hot, or slow molecules, cold. What is really happening on the molecular scale is simply a variation in the degree to which the molecules in the sample are moving, fast or slow. So what about temperature scales? The weatherman tells me that the temperature outside today is 85 degrees. In the United States, this means 85 degrees Fahrenheit. But if we lived in Canada, or virtually anywhere else in the world, the weatherman would be telling us the temperature outside is 29 degrees, meaning 29 degrees Celsius or centigrade. It's the same temperature, but expressed in different scales. It's unfortunate that we don't have just one scale to worry about, but I'm afraid that's life. And you need to be able to convert temperatures from one scale to another. Let's start with the simplest, and thus of course least familiar, temperature scale. It starts at 0 degrees, which is set at the point where the molecules in a sample are not moving at all. Makes sense, doesn't it? If temperature is really an expression of the amount of motion in a sample, then it would be most reasonable to set 0 degrees at this point. This is called the absolute temperature scale, because the 0 degree point is called absolute zero. It's more formally called the Kelvin scale. Now, up from absolute zero, we build temperature intervals in the following way. We choose two easily defined temperature points, the freezing point of water and the boiling point of water at sea level. These are always easy experimental points to achieve, even in the cheapest of laboratories. And then we simply divide the difference between these 2 points into 100 equal divisions. We call each division a degree, and we make that the size of the degree in all temperature ranges. So we build up the degree scale from absolute zero using degrees of this size, and it turns out on this scale that the freezing point of water occurs at 273 K and the boiling point at 373 K. And on this scale, there are no minus degrees. All temperatures have a positive value. The next scale is the Celsius or centigrade scale. It's really just the same as the absolute scale, but with the 0 point set at the freezing point of water. Thus the boiling point of water is at 100 degrees. And so on this scale, absolute zero is really at minus 273 degrees. The last scale is the Fahrenheit scale, the strangest and least convenient. Scientists never use this scale, and so on occasion you may need to convert temperatures in Fahrenheit to the other scales that scientists use. Here's how this scale is constructed. The freezing point of water is set at 32 degrees, and the boiling point of water at sea level is set at 212 degrees. The size of the Fahrenheit degree is then determined by the difference between these 2 points. Now 212 minus 32 is 180. So there are 180 degrees Fahrenheit between the freezing point of water and the boiling point. As you can see then, the degree Fahrenheit is smaller in size than the degree Celsius or the Kelvin degree. Now in the next slide we'll talk about how to convert between these scales. Converting between the Kelvin and Celsius scales is really a trivial matter. The 2 scales are simply offset by 273 degrees. But converting between Fahrenheit and Celsius or Kelvin is a little more tricky. Let's do an example. Here it is. Why don't you read it? Now the best way to tackle this kind of problem is to reconstruct the temperature scales diagram we saw in the previous slide. Here it is again. Now notice 2 things. First, the Fahrenheit scale freezing point is offset from the Celsius freezing point by 32 degrees. Second, the size of the Fahrenheit degree is smaller than the size of the Celsius degree. If we fix each of these differences in sequence, we'll arrive at the Celsius temperature, which corresponds to 56 degrees Fahrenheit. First, the offset. What would 56 degrees Fahrenheit be if the freezing point of water on the Fahrenheit scale were at 0 instead of 32? Well, that would be like sliding the scale down by 32 degrees, right? Let's do that. 56 degrees Fahrenheit is really only 24 degrees Fahrenheit above the freezing point of water. Okay, that takes care of the first step. Now what about the size of the degree? Well, just how much smaller is the degree Fahrenheit? We can readily figure that out by comparing the value of the temperature range between the freezing point and boiling point of water on the 2 scales. That difference on the Fahrenheit scale is 212 degrees Fahrenheit minus 32 degrees Fahrenheit, or 180 degrees. On the Celsius scale, it's 100 minus 0, which is 100 degrees. Thus we see that the conversion factor between the Fahrenheit scale degree and the Celsius scale degree is 100 degrees Celsius over 180 degrees Fahrenheit. If the temperature in Fahrenheit degrees is 24 degrees higher than the freezing point of water, then the temperature in degrees Celsius is, using dimensional analysis, 24 degrees Fahrenheit times 100 degrees Celsius over 180 degrees Fahrenheit, which equals 13 degrees Celsius. Now how do I change the temperature of an object? To discuss this question scientifically, we need to define a couple of terms: system and surroundings. Take my pan of water here. Since that's the object I'm interested in studying, I call that my system. Everything around it that might affect it is called the surroundings. Not profound, but useful. So, I want to heat up my pan of water. That's my system. Heating it up means getting the molecules to move faster, and that means bringing energy in from the surroundings. There are several ways that I could do this. I could microwave it, I could set it out in the sun, I could stir the daylights out of it, or I could use the more common approach, and that is touch it with something that's hotter than it is, like a flame, and that's what I'm doing. Now there are 2 ways that chemists model what happens in this sort of situation, and which model we use depends on what we're trying to accomplish. Scientists often do this, you know, having different ways of describing a system and using whichever one is the simplest to satisfy the need at hand. The first model is to think of what is happening on a molecular level. The molecules in the flame are moving very fast. They bump into the atoms in the pan and cause them to speed up, in other terms, to get hotter. And these, in turn, bump into the water molecules, causing them to speed up and get hotter too. This model helps us envision what is really happening. But unfortunately, it doesn't help us calculate how hot the water will get. There's another model that helps us do that. It's the heat model. Heat is energy transferred between a system and its surroundings. We can measure energy and relate the amount of energy transferred in or out to the temperature change we expect to see in the system. We can't easily do that with the other model. So let's see how this heat model can work for us. Let's say we know how much energy it takes to heat the water in this pan by 1 degree C. And let's say we know how much energy we can get out of burning 1 milliliter of natural gas. Then we could calculate how many milliliters of natural gas we'd have to burn to bring this much water to a boil, wouldn't we? Now let's be honest, no one would really sit down to figure out how much natural gas he'd need to boil a pot of water, not even me. But see the principle? If I were a chemical engineer and I wanted to know how many tons of natural gas I'd have to buy to heat 1,000,000 gallons of water to the boiling point, this could be really useful. The principle's the same, so let's try this simple example to illustrate. We focus our attention on water because it's so basic to everything around us. We'll begin by defining a unit of energy, the calorie. You've heard of calories before, right? Especially if you've been watching your weight. A calorie is defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree C. So if I have 1 gram of water and I transfer 1 calorie of heat to it, its temperature will rise by 1 degree Celsius. We say that the specific heat, or specific heat capacity, of water is 1 calorie per degree per gram. So how many calories of heat would I have to add to 10 grams of water to raise its temperature by 5 degrees Celsius? Well, 50, right? If we look at the question by dimensional analysis, it works out as follows. Now, what if I have not water in my pan, but a big chunk of gold? I wish. It turns out that gold has a much lower specific heat capacity than water. Specifically, it's 0.03 calories per gram degree C. So for comparison, let's figure out how many calories of heat I would have to add to 10 grams of gold to raise its temperature by 5 degrees C. Again, if we look at the question by dimensional analysis, it works out as follows. Wow, gold heats up really easily, doesn't it? It takes a lot less energy in the form of heat to heat it up than to heat up the same mass of water. A common and very interesting kind of change we see in nature involves the so-called changes of state, like water freezing or boiling. We can apply the heat model to these systems to very effectively describe quantitatively how much energy is involved. Take the boiling of water, for example. First, let's make an important distinction between water which is boiling and the situation where we are simply heating liquid water. When we heat liquid water below its boiling point, we are changing its temperature only. When the water starts to boil, we're still heating it, but the temperature doesn't change. All the heat energy we are inserting is being used not to change the temperature of the system, but to change its state. That is, to change it from a liquid to a gas to water vapor. It always takes the same amount of heat to boil a gram of liquid water, 540 calories to be exact. And it takes 80 calories to melt 1 gram of solid water, which of course most people call ice. Every substance has its own unique heats of vaporization and melting. Oh, and by the way, melting is technically called fusion. Now here's the interesting part. If 1 gram of ice has to take in 80 calories of heat from its surroundings to melt, conversely, 1 gram of water has to give off 80 calories of heat to its surroundings to freeze. This idea takes most people by surprise. It seems somehow counterintuitive that when water freezes, it gives off heat to the surroundings. But it does. 80 calories per gram, in fact. And the same happens when water condenses from the gas to the liquid. In this case, a gram of water gives off 540 calories when it condenses from the gas, called steam, to the liquid. Now you might want to ponder these ideas in a quiet moment. It turns out we have special names for processes in which heat is introduced from the system to the surroundings and vice versa. Exothermic and endothermic. The boiling of liquid water is an endothermic process because heat is transferring from the surroundings into the system, hence endo. Get it? And the condensing of steam to liquid water is an exothermic process because heat flows from the system, the steam, to the surroundings, which is usually, of course, the air. So why don't we carry out an interesting experiment? Why don't we see what happens when I put this pan of ice cubes on the stove? I'll set aside my pasta water for a minute, and let's assume that the ice starts at minus 30 degrees Celsius. Here we draw a plot describing exactly what happens. We call this kind of plot a warming curve. On the x-axis we plot time, and on the y-axis we plot the temperature of the contents of the pan. Now, as time goes by, we continually heat the contents of the pan at a constant rate. So keep that in mind. All along the plot, heat is being added constantly. At the outset, you see the temperature of the ice rise at a constant rate. The ice doesn't melt, it just gets warmer. Then, when the temperature reaches 0 degrees C, the ice starts to melt. Notice that an interesting thing happens on the warming curve. The temperature stays at 0 degrees C until all the ice is melted. During this period, all the heat is being used to melt the ice, not to change its temperature. Once all the ice is melted, the temperature begins to rise again, and it keeps rising until the liquid water reaches 100 degrees C, its boiling point. Now while we're waiting for the water to heat, notice something. The liquid water isn't warming up as quickly as the ice did. That's because the specific heat capacity of liquid water is about twice as large as that of solid water. That is, we have to add about twice as much heat to liquid water to warm it up by 1 degree C as we must add to solid water to warm it up by 1 degree C. So that's why the slope of the liquid water warming graph is only about half the slope of the ice. Now, once the liquid water reaches 100 degrees C, we once again see the warming curve flatten. All the heat is going to boil the water, so the temperature stays put until all the water has boiled away. Now just for interest, let me ask what impact these concepts have on the boiling of pasta. Well, one lesson to be learned is that once your pasta water is boiling, it's going to stay at the same temperature as the pasta cooks. What if you were in a hurry and wanted your pasta to cook faster? Would it do any good to turn the heat up on the stove? No. Turning up the heat on the burner will not raise the temperature of the boiling water, which is what is actually cooking the pasta. The water may boil away faster this way, but the pasta will still be cooking at the same temperature, and will therefore take just as long to cook. I'm afraid you'll just have to be patient.